So hello all and welcome to another installment of the University of Alberta Geotechnical Graduate Seminars. I hope everyone is keeping warm and productive in this frigid weather. A couple of brief announcements today. A Women in Geoscience panel event is being jointly hosted by the U of A Geotechnical Centre, WISEST, the U of A CGS Student Chapter, and the United Nations Association in Canada Edmonton branch next Tuesday, February 16th at 5 p.m. For more information, you can contact either myself or Vivian Jang, or you can visit the events page of the U of A Geotechnical Center LinkedIn account. I'll post a link in the chat box for everyone. Additionally, Dr. Franco Oboni with RISCOPE will be providing a presentation to graduate students at the U of A on March 8th in regards to integrated hydrogeological environment restoration of landslides affecting a large asbestos mine dry tailings dump. A sign-up link and further information will be provided in the coming weeks. So today we are once again lucky to have another heavyweight from the Canadian geotechnical industry, Dr. Dennis Becker. Dr. Becker has too many accreditations to go through in this intro, but I will try and do my best to do him justice. He is currently a principal and senior geotechnical engineer with Golder Associates, with over 40 years of national and international experience on numerous large-scale civil engineering resource development projects. Dennis has substantial experience with all aspects of geotechnical engineering, with expertise in site characterization, foundations, stability of slopes and excavations, earth dams and tailings management, liquefaction potential evaluation, soil structure interaction, ground improvement, specialized geotechnical analysis and modeling, and of course, fundamental soil behavior. Dennis is an active member of many geotechnical societies, is an adjunct professor serving on the advisory council of 3 universities, was a chair of the NSERC Civil Engineering Grant Selection Committee, a chair with the Canadian Geotechnical Research Board, has served on numerous technical committees, and even was the co-editor of the 4th edition of the Canadian Foundation Engineering Manual. He has received numerous senior awards, including awards from the CGS, Engineering Institute of Canada, and Canadian Society of Civil Engineers. Dr. Becker's presentation today will touch on testing in geotechnical design. The presentation will describe and discuss geotechnical testing as it pertains to the design process from a consulting practitioner's perspective of the current state of practice. The role, objectives, types, and interpretation of testing, limitations, and recommended good practices will be presented. Please join me in welcoming Dr. Dennis Becker.
Yeah. Thank you very much, Kevin. And can everyone hear me?
Seems good on my end.
Yes. Okay, thank you. Anyway, it's my pleasure to have been invited and privileged to be invited to present this seminar for testing in geotechnical design. The button, there we go. So brief agenda. So I want to talk a bit about the role of geology in geotechnical engineering, briefly about the design process, the geotechnical circle concept, as I call it, which is really a framework of linking geotechnical testing and whether it's in the lab or in the field, and theoretical considerations. Talk about empirical correlations, some testing applications, and end with some key messages. So I like this quote from Carl Jazagi. It took me 2 years of strenuous work to discover that geological information must be supplemented, by numerical data, which can only be obtained by physical tests carried out in the laboratory. This was one of the first statements about recognizing the importance of testing. He had specifically mentioned laboratory, but I think it equally fits in situ and field performance testing. And there's this extreme importance of linkage between geotechnical engineering and understanding geology. Carl Jazagi and others, geotechnical engineering pioneers, always worked in the background of geology. And it's very important to have that linkage of understanding geology and the insight that it provides to us geotechnical engineers with regards to ground behavior. R.F. Leggett, in his book Geology and Engineering, discusses the important interrelationships between geology and geotechnical engineering. If you haven't read this book, you should do so. It's interesting, although given his writing style, some of the sentence structures are a bit long and it's difficult to understand. But anyway, that's just my private critique of an otherwise excellent book. And the other message, the framework I want to leave as a backdrop is a statement I presented in my recent CGS Hardy address, in that statistics, probability, and reliability are useful tools if properly applied, but they must not become a substitute for understanding geology and geological depositional processes, fundamental ground behavior and theoretical considerations, loading conditions and failure mechanisms, and engineering judgment and experience. This slide which I borrowed from Wong et al., talks about three, I refer to it as 3 legs to a stool, in terms of you have your geological model, which relates to geological processes and landscape formation, those types of things. And then you feed into a ground model, which really is defining stratigraphy and the type of ground, soil and rock types you have. And then the geotechnical model, which is applying some numbers to it in terms of engineering properties. And you'll see that there's arrows going in all directions. So these 3 things are fundamentally interrelated, and any testing program should keep this in the backdrop. So many of you have probably seen this slide if you've listened to me talk before, because I've presented a number of times, but I think it's quite a useful slide in terms of setting the stage for the geotechnical design process. This shows a slide for a building, but it could have...
Dennis, we're not seeing your slides, or at least I'm not seeing your slides, so I'm not sure if everybody else is doing it.
Oh.
We see the video is on you.
For how long? How long has this been?
I see the slide.
Yeah, me as well. I think it's just you, Dr. Martin.
Yeah, we can.
Maybe you need 2 screens. Maybe you don't see the right screen.
Sorry to interrupt, Dennis. Go.
Oh, not at all. Hopefully, yeah, no one wants to look just at me through this entire presentation, but I understand most people are seeing the slides, correct?
Yes.
Yeah, it seems so.
Okay, good. Okay. So as I was saying, this applies to buildings, but it's also applicable to any project, dams, bridges, or what have you. You start off with whatever the project is and the client's needs, etc. For this case, it's to design a suitable foundation. Usually design is controlled by a code or manual guidelines, which will have some recommendations on testing as well. And it will feed into what's, the load effects on this building. And again, testing played a big part to come up with what are those load effects. It feeds into a calculation model. And again, testing was a key part of that. And testing is very obvious in this upper part where you're doing the site investigation work, drilling boreholes or doing CPTs, and then doing some interpretation, which then brings you into the geotechnical model. So the layers of ground and engineering properties, and that feeds into an analysis assessment, as does this calculation model and load effects. And then, that whatever number comes out of that particular analysis isn't really the end of it. it needs to go through an assessment, engineering experience, and judgment, and then out of that will come out what is the appropriate design. So there's some key considerations in support of any design approach, and it's applicable to all projects. Again, my first point is it's important to understand the geological setting. And this, I think, can be, or a lot of times is more important than the method of analyses and calculations. You should take away from this lecture will be, or presentation will be that don't forget about geology. It's very important. The other aspect as geotechnical engineers, we have to make the most of limited site investigation data and honor all the data. What I mean by that is that you can't ignore something because it's convenient to do so. If that, if you interrogate that result and you find the test was conducted properly, there's no reason to discount it. So you have to keep that data point and make sure you assess how it might affect your analyses and design. I always tell my younger colleagues is that you need to spend time to develop an appropriate geotechnical model. When I was a young engineer, I just wanted to rush into the analyses, and you really shouldn't do that. You need to spend the time to make sure you got the facts right in terms of developing your borehole record and things like that, because at the end of the day, if something goes wrong, you will be judged. When I say you, a geotechnical engineering firm will be judged by how representative and correct their borehole records are. Another aspect that I've dealt with or that I use is, capture the essence of the problem and the key controlling design issues. And you start off with simple testing, simple analyses, and then you increase that level of sophistication only as needed or as the project requires. So start simple and move on from there. Don't start something complex from the get-go. And it's important to have a consistent theoretical framework in which to assess and interpret your test results and the ground behavior. I've always used critical state soil mechanics and yield envelope concepts and those types of things, but that's not the only framework in which to deal with, but it's important that you do have a theoretical framework in terms to assess testing results and ground behavior. And then the element of good engineering judgment and experience, because as you know, they say good judgment is usually the result of experience, and experience is frequently the result of bad judgment. So referring back to Leggett, he pointed out that there's basically three primary branches in geotechnical engineering. There's the theory and theoretical approaches. There's your site investigation to get quality samples, to try to obtain the ever elusive undisturbed samples. It's difficult to truly achieve that because even the method of drilling a borehole or pushing a cone, really there's always some sort of disturbance effect associated with that. And then the third part of it is laboratory testing. So in situ testing, whether it's CPTs or dilatometer, pressure meter, it was developed and occasionally used starting in the 1980s, just as I was starting my practice. And but routine use really only started around the mid 1990s. And since then, I think there was a sense that in situ testing rules, that you should rely on in situ testing rather than sampling and laboratory testing. But over the last few years, my sense is that the need to obtain samples and do laboratory testing, I think it's making a comeback. I think the industry should never get to a point where you never obtain samples, you never get your hands dirty by looking at them. It's a very key part of the process. And I refer this as the geotechnical circle concept, and it fits into what Leggett was talking about, where you have your theoretical aspects, which is constitutive laws and stress field and yield surfaces and the like. That fits into what type of laboratory testing you would do, which then fits into in situ testing. And then the results from in situ testing also feeds back into what you would do on laboratory testing. So it's like layers of an onion, where you start at the outer part is understanding your project client needs. You develop a site characterization program, you move into testing conditions, and then that feeds into site assessment, as does your field and in situ testing. So this geotechnical circle concept, I think, is a very useful aspect to keep in mind. And the whole process is very iterative, as shown by this slide with this flow chart. We've already talked about understanding project needs and those types of things. You review existing site information. You should sort of develop a conceptual model, design a testing program, and then you get into the iterative part of where you collect the data, you examine, interrogate it, and does it fit within your theoretical framework? And if all the results are consistent in that, great, you're done, and you can go in and report your findings and establish your geotechnical model. The answer to that is no. You may, and there's no scope change. You go back up and you go through that loop until you finally can say yes. But if you've come across something that might be different, there could be a scope change. Well, then you go in, modify your testing, and then jump back into the process and start over. Well, not start over, but just go through the process. So some of my thoughts upon what forms a meaningful value-added test program. And first one here, it's you have to understand the limitations and advantages of your various tests, whether it's in situ laboratory or field performance. It's like a toolbox with different sets of tools, and some tools are better suited for a particular problem than other. And you need to have thoughtful and adequate planning that is based on a good theoretical framework from which that you would use to interpret and interrogate the test results. The third bullet here is how much you get out of a test program really depends on how much care and thought you put into designing the test program. If you haven't given it a lot of thought, chances are what you get out of it is commensurate with not giving it a lot of thought. So I stress this particular point. You really have to give it careful thought in terms of what it is you need to obtain and what's the best way of doing it. It's good practice to simulate in situ and loading conditions to the fullest extent practicable. For instance, in landfill work, for something, if you have leachate type of as your fluid, then it's good to have that into your laboratory tests program, but you should do it in a laboratory that has a fume hood, or else it could get rather nasty. And again, the results are only as good as the sample and care when performing the test in terms of trimming the sample and things like that. If you trim it and you've done a good job and then it fell on the floor as you're going to your triaxial machine and no one's looking, don't pick it up and continue with your testing, because that's not going to get you anywhere. You have to start over. Lots of data is not necessarily a good thing. It's more emphasis on quality than quantity. Again, I've already talked about don't ignore outliers. And it's important to start building up a database of statistics and reliability to develop a geotechnical database for mean value and coefficient of variation. And the final comment here is quality is everyone's responsibility. And by that, I mean it starts from the engineer or whoever's setting up the field and lab testing program to the people who are executing the program. Everyone should have a view of doing the best that they can to achieve quality. The next few slides will talk about examples of testing that supported the development of theoretical considerations and applications in practice. The first one is state parameter developed by Ken Bean and Mike Jeffries, and that was developed in Boulder, Calgary in the early 1980s from the need associated with the Beaufort Sea. And the concept is quite simple. The details are, you have to be rigorous in the details, but basically you can assess sand behavior if you know the critical or steady state slope state line, which is a condition of testing that is at constant volume, a constant void ratio, constant velocity, those types of things. And then you have a condition of, oh, I should mention this is void ratio plotted against log mean stress. So you may have a point A that plots above the steady state line, and the distance that A is from that steady state line, that is the state parameter. And if you're in this region, it's positive state parameter, or it indicates contractive soil behavior. So you may have an effective stress path that does that, where it rises to a peak and then strain weakens, and you typically would have volume excess positive pore pressures and volume decreases. So this is contractive material or potentially liquefiable. Negative state parameters when you're below the steady state, critical state line, and typically this is dilative behavior, and then you would have effective stress paths that swing up to the right. You'd have sort of a strain hardening stress strain curve and increase in volume change. So testing formed a very significant part linked with critical state soil mechanics to come up with this this fundamental concept, which is very widely used in industry today. Another example, this time with clay behavior, is the concept of a yield envelope, which is this big, thick black line. This stress path or vertical axis label is your axial stress minus your radial stress, because sometimes your radial stress or horizontal stresses could be greater, which then puts you into a negative space using these symbols. If you were to put this into sigma 1 and sigma 3 principal stress rate stresses, you would only have the upper part of this curve. But I think it's instructive to have it in terms of horizontal and radial and axial stresses. So you can do different types of testing, to strain control testing or a stress control testing. You can do some odometer work or a stress path coming out here to define your yield envelope. And typically, the part that intersects where K0, this is your pre-consolidation pressure, and the top part of your yield envelope, typically is around 0.2 to 0.25 of that pre-consolidation pressure. And we'll come to that aspect in subsequent slides. When you're in this part of the yield envelope, you're over-consolidated. So you have low strain, high coefficient of consolidation and that type of thing. And in order to have strength gain, you have to have loading that pushes you outside of the yield envelope, or you have to exceed the pre-consolidation pressure. And then once you're out in this area, it's normally consolidated, higher strain condition, lower coefficient of consolidation. So this concept is very useful to understand clay behavior. And the other aspect of this is what's called average mobilized undrained shear strength. I think many of you have already seen this figure where embankment loading, where this part of the ground's in compression, this part's in direct simple shear, and this part is in extension. And typically your undrained shear strength is about 0.22. I've used 0.22 for a long time in my practice of the pre-consolidation pressure. Or you can also put this in a Shansep approach where this stress ratio is a function of your normally consolidated stress ratio, which is your 0.22 or 0.25 number times over consolidation ratio. Testing has shown that if you're doing triaxial compression, the ratio of SU upon PC is about 0.3. Direct simple shear is around 0.2, 0.25 to 0.2, and extension is lower. So as a typical average mobilized strength, your direct simple shear value is not bad. Shown on here is the range of field veins, and you'll see as you get into, and this is plasticity index, as you get testing higher plasticity clays with the field vein, you need to make a correction because it tends to overestimate the strength, and that's to bring it down more in line with the 0.22 number. So if your vein, if the ground that you're testing with the field vein is in the 20 to 40% plasticity index, you don't need to make significant corrections. So next few slides talk about in correlations, and geotechnical engineering has always had relied on empirical correlations. They're very useful, but you have to understand how they were derived and why they were derived. I think the most valid empirical correlations are those that capture the essence of behavior or first order controlling effects. You should always have a theoretical understanding or theoretical basis, physical understanding of what properties you think can be expected to be related. It's important, in my opinion, to correlate undrained response in a test that has undrained parameters, or a corollary of that is drain response in a test to drain parameters. So if you're pushing a cone through a clay, it's undrained, so you should be going to undrained shear strength. The cone is going is drained in its response, such as in the sand, then you would be going to effective stress or drain parameters. And it's important to consider strain compatibility. If you're doing an in situ test such as a dilatometer where there's very small strain, that would be useful for K0 type of thing, but it wouldn't be all that useful for large strain behavior. So as an example of capturing first order effects on the field vein strength, which is a very common test, and when you look at the vein, 90% of the failure surface is along the vertical plane. So you would expect that maybe horizontal stresses would help control the strength that you measure from a field vein, but yet most correlations are done with vertical effective stress. This slide compares whether it's vertical effective stress or horizontal stress, where I've had some sites where I've had pressure meter data or other tests where I can measure K naught. And these are from these tests here. And if you plot SU vein against vertical stress against OCR, you get this type of correlation. And that's similar to the Shansep approach, the equation I mentioned earlier. But if you take that exact same database and now you normalize it with regard to take K naught or horizontal stress into account, that same database collapses down to a very narrow band. And to me, this indicates that you are capturing first order controlling effects on the field vein strength, and that horizontal stresses are important to consider interpreting field vein strengths. That's reinforced by this slide, which again plots SU of the vein against pre-consolidation pressure against plasticity index. I mentioned earlier about the Beerum correction factor for correcting high plasticity clays. And sometimes that correction factor or adjustment factor could be as high as 0.5. And again, the intent is to bring measured values up here down into more in line with the direct simple shear mode. And again, if you take that same database and you plot it with, instead of vertical yield stress or pre-consolidation pressure, you do it in terms of horizontal yield stress, it collapses down into this quite narrow scatter from a soil mechanics point of view in the data, which again, in my opinion, demonstrate that you've captured some of the controlling effects of the test results. And for a field vein test, that's horizontal stresses. So the earlier slide about yield envelopes talked about the importance of OCR and pre-consolidation pressure. They're very important. There's many correlations based on these factors. Therefore, it's important that you have a reliable and unambiguous, I call it certain assessment. Many of pre-consolidation pressure. However, many soils have rounded E-log P curves, and everyone's familiar with the void ratio vertical effective stress on a log plot. And if you're doing the Casa Grande technique, it could be somewhat ambiguous in terms of what is the pre-consolidation pressure, keeping in mind that this is on a log stress. So if you're using a magic marker instead of a 0.5 mechanical pencil, it has to draw your line. It has a big effect on the interpretation. So we need a more definitive assessment of pre-consolidation pressure, which led into some work that I did in the early 80s, again on the Beaufort Sea work, where there was the need to have a better definition of pre-consolidation pressure. And it wasn't that I woke up one morning and said, I'm going to do something clever today. Rather, I was in the lab, but in those days, you ran your own testing. I did all my odometer tests, triaxial testing and that. And I was reading papers on people determining yield from triaxial tests, which is 2-3 dimensions, and sort of said, well, if these people can do it in 2-3 dimensions, I might stand a chance of dealing with it in 1 dimension. So applied the same principle of strain energy, which is just the area underneath your stress strain curve. And this same data in terms of strain energy or work done against vertical effective stress on an arithmetic scale plots like that. And I would say there's little ambiguity of what the pre-consolidation pressure or vertical yield stress would be. So if you haven't used this approach, I would suggest that you try it. I was very pleased when people like Professor Charles Ladd at MIT and others at NGI have said that they now routinely use this technique to determine pre-consolidation pressure. And the other thought I had on days when I guess I wasn't busy enough, if we look at, normally we have our ground surface, we take our Shelby tube and then we take it to the lab, we trim it. Normally we trim what I call a horizontally trimmed specimen, and then that should give you vertical stress, pre-consolidation, vertical yield stress. And I said, well, if I trim it vertically, then I should be measuring horizontal stresses. And to compare that, I had the luxury of having pressure meter data, high quality pressure meter data, to interpret horizontal yield stress. And this is a plot of excess pore pressure versus total cell pressure. And where you start seeing an increase in pore pressure is the yield. And you can see that from the stress strain curve here. And this is a reasonable agreement. The circles are from the odometers. This is from the pressure meter tests. So they have the same sort of trends, and which is useful because then if you want to get an indication of horizontal stresses in that, you can do it by simply vertically trimming tests. Here's my one outlier that I haven't taken out because they couldn't ignore it. So I haven't explained why that happened, but I didn't throw it away. What is known about CPTs is frequently used to get pre-consolidation pressure, because if you have pre-consolidation pressure, you can go into undrained shear strength, such as 0.22 times the pre-consolidation pressure. There's been a lot of work done over the years in terms of that pre-consolidation pressure is a function of your tip resistance minus the total vertical stress, and this function factor F varies from 0.28 to 0.33. There's lots of papers that reference this particular number. But again, I had the luxury working in the Beaufort Sea to have lots of data, and this plot is your cone tip resistance normalized against OCR, pre-consolidation pressure. For each of these data points, was able to have an odometer test to calculate, measure PC. And then we had nearby CPTs. We used to do a CPT and then a sampled borehole not too far from it. And this data is normalized not with regard to vertical effective stress, but it's normalized to mean effective stress, because we also had pressure meter data and things like that. And when you plot up all that data, I started with Beaufort Sea work, but then over the years I've added data from a lot of other projects in which I've worked, and it always fit within the original correlation. And it demonstrates that this relationship of 0.28 to 0.33, I think is valid if you have K naught that's less than or equal to 1.5. But if you have higher K naught situations, then that particular number could decrease. If you plotted this up in terms of vertical effective stress, you would have a very similar trend, but perhaps a bit more vertical, more scatter. Again, the horizontal stress is a key part of controlling ground behavior. And so you should try to consider that when you're assessing engineering properties. Again, this comes out of the field vein. We take the cone data to get SU using an NK, but that's reference to another test, typically the field vein. And what this plot is showing is the effect of K0 and OCR. Typically, we think of the field vein, the NK factor in the range of 10 to 15. And this data spread here shows that that's reasonable if you have normally, a K0 of 1 or less. But if you start having higher K0s, you can have much higher NK values than one would normally be used to. Similarly with OCR, this is showing the difference of NK, again with K0. So having an appreciation of K0 or your horizontal stress field is important in terms of and this goes back into geological depositional histories as well in terms of what K0 value you may have. And you should always keep that in mind when you're looking at your test results. How am I doing? Okay, I need to move on. I think we're okay for time. I'd like to chat a bit about other testing applications such as field performance test. And these are important for design improvement and efficiency of design. It's for field performance verification. Like if you're doing ground anchors, you typically the practice is that you do a proof load test on each of the ground anchors to verify that your design is valid. And again, testing is very important for QA, QC work. And the commonly used tests are, everyone's familiar with them. But I've also added pump tests, geophysics, and those types of things are quite useful. And then we have field performance tests, which are load tests on full-scale units. And then you have physical modeling or smaller bench scale tests, such as the centrifuge. And I'll chat briefly about that in a few slides. The previous slide here is, this is an O-cell test for testing ultimate skin friction and end bearing on reinforced board concrete piles. It's a excellent test. So the full-scale field performance tests, they provide an understanding of the geostructural element in the system. You can get design efficiencies because you can use higher geotechnical resistance factors or lower factors of safety. But if you're going to take the time to set up these tests, then you should take them to failure so that you obtain ultimate values of geotechnical parameters. And then this allows you to refine your design and provides the highest degree of certainty. If you don't take it to failure, you can't really refine your design. It's only a confirmation of a proof that you have at least that particular value, ultimate value of skin friction or lateral pile resistance, as shown by this test, which is lateral load tests on piles. And the concept of why it increases efficiency, if you're not doing load testing, the codes will allow you maybe 0.4 of your ultimate value here, which I've shown in a dashed line, which is estimated. But if you do a load test and you get this particular result, and you notice the estimated RN ultimate value is higher, and then you get to multiply it by at least 0.6. So you've got a very significant increase in your design load. However, I have to point out, a lot of my clients think, well, let's do a test because you're going to get higher numbers. And that often happens. However, there's been cases where you do the test and you actually get lower numbers than what you first thought. So once you do the test, you're stuck with the number. You can't say, oh, well, it's lower, I'm going to go back to what I had before. So doing more testing could be a bit of a double-edged sword, but most of the time it's to advantage. As I mentioned, you can have this increase from 0.4 to 0.6. That's, you say, wow, that's a whopping 50%, but it really doesn't translate into 50% cost savings because there's other things such as redundancy, pile spacing, and other things that need to be taken into account. Field performance tests are very expensive. The full-scale load test could be of the order of $100,000 for one particular test, but they can provide significant cost benefits. So if you're explaining this to a client and owner, use the word investment, that he's investing his money. It's not a cost. Clients and owners are sophisticated. They understand investments. Talk briefly about physical modeling tests. They're needed because a lot of times the behavior of natural soils and rocks are so complex that it can't be captured by analytical and numerical methods alone. It helps gain improved physical understanding of failure mechanisms. It assists in the calibration of analytical and numerical methods. However, small-scale physical tests can usually be done only at one gravity, and therefore you don't always get to model the actual stress conditions that you have in the ground. And there's limited use of physical modeling tests in practice unless you have some very large and special projects. And examples of physical modeling tests are the single and pile group behavior, static cyclic loading conditions, frost heave forces on pipelines. This is a setup of we have a cold room in our Calgary office, and we have programs to measure the stresses in that induced on a pipe due to frost heaving. We've also done work with iceberg scour studies, flume testing for tailings deposition, and overtopping of dams and fuse plug design in dams are useful physical modeling tests, and the centrifuge. So the centrifuge, it's increased significantly over the past 25 years. I believe U of A, Rick Chalaturnik has a centrifuge now at U of A, and I'm sure there's a lot of excellent work coming out of that. The advantages is that you can produce more realistic, higher stress fields associated that you would have in the field, whereas just a small scale test, a static test only allows you to test under 1 gravity and not 4 times gravity or whatever the case would be. It helps shorten the time when you're modeling problems with a effective advective flow and those types of things. Yeah, but it's used mainly as a research tool, but it has had some limited use in practice. Kevin, is a bit of a time check. I see it's 10 to 1. I was going to talk briefly about using the centrifuge at the Confederation Bridge, but if you want to set some time aside for questions, I'm okay with that as well. And I would just skip to the some of my key messages.
Yeah, I think you can go ahead and jump the centrifuge model in if you feel like it.
Okay, so but this is over at 1, right? People have to head off and those types of things. I'm just cognizant of the time.
We can go a little later if you have the time. It depends on your schedule. You're the guest of honor.
Oh, okay. Well, you should never invite me to speak longer. But I'm more concerned about others. So okay, I'll just press ahead. And again, my apology for this being a bit longer than I thought it would be. But I did want to share this experience on the Confederation Bridge. And I have to admit that I was a bit of a skeptic going into it. But I think it, you know, I've experienced that it has many attributes and is very positive in terms of complementing what one would normally do in a design process. And on the Confederation Bridge, where we had ring and oval shaped footings, it certainly helped provide an improved understanding of the failure mechanisms of these footings that were subjected to very high load eccentricities and inclination effects due to the ice loading. And you can see the bottom is in the winter, and you can actually see the ice sheet flowing and leaving a bit of a wake in behind the pier. So there's very substantial horizontal loads applied high above the base of the footing. And it was also, it being centrifuge modeling, was very useful in helping us understand when we could do more simple analyses, such as 2D analyses, and where we needed to do more sophisticated 3D analysis, going back to my comment earlier that, you know, start off simple and only get more sophisticated as need be. This sketch shows the configuration of a foundation unit. It's a hollow type of structure, ring, and as I said, there's very high ice loads, which then has a moment associated with that, and so there's quite the concern of this structure here just sort of tipping over as much as sliding. And we started out, so in reality, we have circular ring footings and oval rings. And when we have these horizontal loads, there's a consideration where the red here is actually your contact, and the lighter area is where you would actually have liftoff or whatever due to that horizontal load and moment. And that was first handled with just simple models of equivalent square footings or rectangular footings. And we did centrifuge testing. And in the end, we actually did do some 3D finite element analyses as shown in this sketch here. And now the ice load here is going in the other direction. But anyway, you can see that the model was actually showing that you have this sort of tilt of the structure and not full contact everywhere along the base of your foundation. So C-Core did some excellent centrifuge testing for us on different models, and they came up with quite an ingenious method of applying lateral loads and things to simulate the ice loading and those types of things. And then the results of this came out where it showed where we actually did have concentrated loading and these spaghetti markers, and they truly were spaghetti. It was just simply the pieces of spaghetti were inserted into the into this ground model before it set up, and then it was a very useful tool to identify what deformations were happening and what a failure mode may be associated with to take into your analytical and numerical modeling. So I became a believer with the work on the centrifuge, but again, it took a from a practice point of view, it took a large project. So to wrap up, I have a couple of key messages. I think you've already understand the first two bullets. I've talked about those already, about making sure you don't forget about geology. You have to understand the geological depositional histories and other aspects of fundamental ground behavior, and that in your analyses. The geotechnical circle concept, I think, is very useful, and it demonstrates that testing is an integral part of design. It could be iterative, and it fits into this philosophy of framework of linking testing with theoretical considerations. And it's useful, if not mandatory, to have a consistent theoretical framework that you're going to use to interpret and interrogate your test results. You can't just do a test and say, what's it going to, let me see, let's wait until what the test says. You really have to have a basis of setting up the test and then see how your test result fits in with your hypothesis. Again, this thing of you get out of a test program the thought and care that you put into setting up the test program. When you're developing correlations, it's important to make sure that your correlation captures first order controlling behavior. I mean, you can take anything and plot it against something else, but and then see what comes out of it. But it's always more meaningful if you think ahead of, okay, I have this value, this parameter, and this parameter. They should be correlated for this reason, and then plot the results to see what you have. Again, this concept of you should, if you want to go after undrained parameters, then you should base that on undrained tests. It's a bit inconsistent to go to using a drain test to go to undrained behavior, although you will see lots of correlations that are published in that regard. But if you really want to capture the essence of the correlation, you have to match up undrained testing with undrained parameters. For field performance testing, I think if you're actually, you should, whenever you can, take those tests to failure so that you truly understand what your ultimate values are. And once you know the ultimate values, whether it's skin friction or end bearing, to use the pile example, then you can refine your design. And again, this thing of field performance tests are very costly. So you should describe them in terms of an investment to the project and not simply as a cost to the project. And that wraps it up. And again, my apologies for speaking a bit longer than I intended. I should have stayed to a script, but I usually don't work from a script. So anyway, thank you very much. And for those who may still be around, I'm willing to take questions.
Thank you so much, Dr. Dennis Becker, for the presentation. We still have time for some questions. And my name is Lan, and I will be hosting the Q&A session for our graduate seminar.
Okay.
So nice to meet you. So let me follow the questions in the chat box and I read it to you one by one. The first one is from, I guess it's from Jeremiah, the lady from Ireland. She was asking, could you provide some example of a project you had where large-scale load tests were recommended or used?
Sorry, large scale
And load tests.
load tests?
Yes.
Well, the first time I came across the and used the OCell was the work on the Confederation Bridge. There was some the approach peers. We did load testing on the mudstones to come up with or to develop ultimate values for skin friction and end bearing. But I've used them on several P3 projects, public-private partnership projects in terms of highway projects where, you know, there's a lot of bridge structures and those types of things. So the benefit, it certainly, on those projects, it was always worth the investment of spending the money to enhance the design and being able to demonstrate that you could use higher ultimate values than one normally may see from references in textbooks or guidelines.
Thank you for the answer. Let's move on. We have two questions from Don. The first one he asked is, we could obtain friction angle and cohesion from many kinds of tests, for example, like CPT, SPT, or pressure meter test, and the lab test too. But in many cases, they're usually different from one another. So in your opinion, data from which test is the most reliable one and we should use?
Okay, so if I understand the question, it was related to shear strength. So I'm very much a believer of placing more emphasis and credence on a direct measurement as opposed to correlations. So if I was after a more Coulomb failure envelope for material, I would do my best to get high quality samples and do triaxial testing or direct simple shear testing. If I wanted to get a good handle on undrained shear strength, then for undrained shear behavior, which controls a lot of design, especially in dams on materials that are contractive. So from a strength point of view, I prefer laboratory testing on high quality samples compared to indirect methods or such as CPTs, because there's an extra step in there that because you have to correlate the tip resistance or something with shear strength. So my apologies if I misunderstood or misinterpreted the question.
No, that's correct. So he has another question. Could you suggest a good way to estimate the value of a parameter NKT in CPT test?
NKT?
I think it's, yes, it's a parameter NT or NKT from CPT test interpretation. Or
yeah, well, if I understand correctly, I think your CPT, I mean, you're measuring tip resistance, skin friction, and pore pressure response, right? And then from there, you need to go into engineering properties. If you're going after undrained shear strength, then use the NK value, as I mentioned in my presentation, but and in my experience, that value can vary anywhere from 5 to 30. And it's not always 15 or 13 or that type of thing. So I think you have to understand, you need a reference test. And a lot of times it's the field vein, but you also have to understand that sometimes the field vein tests may not be perfect either. It works well for clays, but if you're in more silty materials or if you're in tailings, the field vein test with the normal speed that you rotate the vein, it may not be fast enough that you're actually getting undrained behavior, right? So you have to at times question your reference test because as I said, in some tailings, the field vein test probably is not truly an undrained test because of the hydraulic conductivity of the material, etc., perhaps being too high for the standard rate of rotation. So I've been involved in projects where we actually changed the rotation of the field vein, or we increase the rate of penetration in your cone CPT testing to see what effect it has in terms of trying to better understand undrained shear strength. Right. However, but it's, you have to be careful because everything is standardized. For CPTs, 2 centimeters per second, and then I forget what the rotation is. ASTM has, got standards in terms of what you're supposed to apply, but I think you should always think about, given the soil or the material in which you're dealing with, does this rate of penetration or rate of rotation, is it truly undrained or not?
Yes, that makes sense. Let's move on to the next question from Kevin. He said, you mentioned that you should use drain tests to capture drained behavior and undrained tests to capture undrained behavior. What is your opinion on engineers using consolidated undrained structural testing to characterize things like weak shear for its strength parameters?
Sorry, I didn't catch the last part. To capture.
He's wondering, what's your opinion to use consolidated undrained structural test to characterize the strength parameters of weak shear?
Oh, okay. Yeah, okay. Good question. Instead of, I think my preference there for that type of material would be to go with direct simple shear testing as opposed to triaxial testing. I think one has to consider, the composition of the material in which you're testing, and if it has stronger and weaker layers, then a triaxial test captures the let's say the overall strength of that material, but it may not capture the weak element of the particular material. If I've understood the question, as a analogy to that, I've always been very leery of using field vein tests in varved clays or interlayered clays because again, you have a vertical failure surface, and when you turn the vein, it's shearing the weaker clay layers and the stronger silt layers, right? But in reality, if you have a failure in the ground, it's going to shear along the weakest layer that you have in the ground. And therefore, in those layered materials, one has to be very careful about using, let's say, the field vein tests.
Okay, thank you. Please bear with me. We still have 3 questions in here. And the next one is from Dallas. And this question is about the horizontal stress. In his opinion, his experience, he doesn't think many practitioners measure K0. Do you see this as a gap in industry? And when estimating K0, do you have a preferred field test method? For example, like CPTU, pressure meter, or dilatometer test?
Okay, good question. For K0, if you're after K0 or in situ horizontal stress, then I think the test I would go with is low strain testing. So that's a dilatometer would be useful. Pressure meter testing is useful. So K0 is a very important parameter, and we have to understand what it is, but I'm going to say what it is not. K0 in the field is not the Jakey equation 1 minus sine phi. So I know what it's not. If you and what I mean by that is everyone wants to use the Jakey equation 1 minus sine phi as an estimate of K0. And yeah, there's very little basis for that. It's a correlation that's been developed, but I would shy away from use of that particular equation because it deals with incremental K0, not necessarily the K0 that's actually applicable in the field. So I don't know if that answers all of the questions, but I that's good that was brought up because I did want to get to the point of reservation of using 1 minus sine phi as K0. If K0 is really important, and it is in many situations such as tunnels and other applications, if it's important, you should go out and measure it, not necessarily assume it.
Thank you. It does answer the question. And I also had a question about, particularly about your slide, page 23.
Page
23. Actually, I can just describe you briefly. When you compare the yield strength interpreted from odometer test versus pressure meter test, how does the difference of boundary conditions play a role in these 2 tests?
Under what conditions?
How does the difference of boundary conditions, like a stress path in these 2 tests, play a role to affect the interpretation of yield strength?
Oh, yeah. I mean, my point there was, I mean, if you're after K0, then yeah, you should measure pressure meter tests or what have you. What I was getting at with that comparison is if you, as an indication of K0 and horizontal yield stress, I think you can get some insight from the what I call the vertically trimmed odometer specimen. And but again, you know, if I had my preference and had the wherewithal to do it, then I would use in situ testing to measure K0, not inferred from laboratory testing. But the odometer is still better than 1 minus sine phi.
All right, thank you, Dr. Dennis.
If anything, people should understand that I'm not a big fan of Jakey equation for in situ K0.
Yes, always to be better to measure something than estimate with empirical equation. I have last question from Mayu. The question is, he thinks or she thinks a critical state parameter should be a framework to conduct our analysis. What do you suggest to encourage more engineers to use?
The state, I didn't catch the first part, the state parameter?
Yeah, critical state parameter.
Oh, I mean, I suppose I'm biased, but I think critical state soil mechanics offers a lot of useful insight in terms of understanding ground behavior. So I think it's a very good technique, but you know, you have to keep in mind, I've known and worked with Mike Jeffries and the late Ken Bean for a long time. So their influences have rubbed off on me, but certainly I think it's excellent. But I will say there are also limitations to critical state or the Norsand model and those types of things. So I think you know, you have to recognize that everything is not perfect, but you have to I think it's a good framework. Let's just leave it at that.
Thank you so much. I think that's all the questions I have here. And thank you for answering those questions and again sharing your understanding, your work.
Okay, my pleasure, and delighted there was some questions. It's always a reflection of whether there was interest or not, or whether everyone is left. See, that's one of the things about making a presentation virtually. You can't read the body language from people in the audience in terms of did they picking this up, or do I move on, or are they yawning, are they asleep, you know.
Yes, absolutely true. All right, given the time we had here, and I think you're already over the time.
Yeah,
I would like to thank you again for spending time with us, and thank you for everyone being in this seminar.
Okay. Well, again, thank you. My pleasure and privilege to be asked to make this presentation. Thank you.
Yeah, thanks a lot, Dennis.
Thank you.
Okay.
Have a great day.
Everyone have a good day. And if you're in Alberta, keep warm.
Indeed.
Okay. Bye-bye.